Our next reaction to look at is hydration, or ways to add water. So the first thing is, the first reaction we looked at with alkenes, the use of aqueous acid, is not used much for alkynes. Why not? Well, just in general, it's too harsh. And while it certainly might do what we want, in other ways it will just chew up and destroy a lot of different molecules. So we go back to oxymercuration. Which uses slightly different reagents here. Mercury sulfate and sulfuric acid. And the main difference in this mechanism, at least at the start, is that instead of forming a three-membered ring, we form a cation. And the main reason, again, is a three-membered ring is unstable enough. But if we try and put an alkene into a three-membered ring, they're even less stable. From here, water will attack that cation. To give us an intermediate that looks very similar to what we saw in the alkene oxymercuration. It loses a proton to then give us the alcohol. This is where this reaction changes, though. It turns out that this molecule is not stable. And so in the presence of acid, the presence of the conditions it has, we don't even need the sodium borohydride. That mercury group just gets replaced by a hydrogen to give us this compound. This is known as an enol. We will learn later on that OL is the ending that we use in nomenclature for alcohols. So what we have is an alkene directly attached to an alcohol. We call that an enol. But enols, it turns out, in many cases can't be isolated. And if you have acid or base present, and in our starting conditions we have acid present, an enol will get converted to the carbonyl. Now these two compounds, the ketone and the enol, are known as Tautomers, which basically means that they are rapidly equilibrating isomers. They are not resonant structures, but they are two isomers that under the right conditions can be interconverted with each other. And so under acidic or basic conditions, enols in almost every case will get converted to the carbonyls. Why? Well, in general, the carbonyl is more stable. And so when you do oxymercuration of an alkyne, turns out while you do initially end up with the alcohol and the more substituted carbon, the final product is actually a carbonyl at that position. Now this last piece, the enol converting to the ketone, that's a reaction that we will study in much more detail in Organic 2. What about hydroboration? Is the same thing true? So we start the reaction out exactly the same way. We use borane THF. And as before, that puts the boron on the less substituted carbon and the hydrogen on the more substituted carbon. Also, as with alkenes, this will happen a total of 3 times until we've replaced all of the hydrogens on the boron with alkyl groups. So again, this is an anti-Markovnikov process. Now, hopefully you recall at this point what we did with alkenes in that reaction was we added peroxide and base. And the peroxide and base was able to convert our alkyl borane to an alcohol. And it does the same here. But once again, just like with the oxymercuration, we've made an enol. And we said that enols with either acid or base get converted to carbonyls. And in order for this step to occur where the boron gets replaced by an OH group, we have to add base. So we have an enol, we're in the presence of base, and that enol will get converted to the carbonyl. Now you may notice with some of these reactions of alkynes, I'm not really showing as many applications or examples as I did with alkenes. And that's because these alkynes don't really do as much in terms of application. We don't really find a lot of alkynes in nature. So we don't have as many interesting examples. All right, so under standard conditions, and by standard conditions I mean the same set of conditions that we did with alkenes, hydrogen gas and palladium on carbon, our alkyne will get reduced all the way to an alkane. And with this reaction, there's no way to stop it at the alkene. But that is something we might want to be able to do, have the ability to form an alkene. And if we're going to form an alkene from this, we'd have 2 options, cis and trans alkenes. So we have 2 main questions here. First of all, can we do this? And then second, which alkene do we get? Do we get the cis or do we get the trans? And can we control that? So it turns out that we can do this, and depending on the reaction conditions we use, we can choose whether we get the cis or the trans alkene. So one way to do it is to use something known as Lindlar's catalyst in the presence of hydrogen gas. Lindlar's catalyst is palladium. Now instead of on carbon, it's on calcium carbonate. And then we also add lead tetraacetate and quinoline. Which is this structure drawn here. Quinoline is actually something that we'll talk about later on in this course because there's a lot of quinoline derivatives that have very, very useful biological activity. In fact, a lot of quinoline derivatives are used in anti-malarial drugs. But the role of these extra pieces, the lead tetraacetate and the quinoline, is they poison or deactivate the palladium. And in fact, they get the palladium to a point where it can react with an alkyne, but not with an alkene. And so the result here is that if you use Lindlar's catalyst, you can convert your alkyne to an alkene, but it won't go any further. And specifically, using Lindlar's catalyst gives you the cis alkene. Now, what if we wanted the trans alkene? Well, in that case, we use a reaction known as a dissolving metal reduction. So for that, you take an alkyne and you add lithium metal in liquid ammonia at negative 33 degrees Celsius. Why negative 33? Well, that's the approximate point where ammonia becomes a liquid. So below negative 33, ammonia is a liquid. And for this reaction, it favors the more stable trans alkene. So overall, when it comes to reducing alkynes or hydrogenating alkynes, you have three options. You can use palladium on carbon with hydrogen and you get the alkane. You can use the poison catalyst, Lindlar's catalyst, and get the cis alkene. Or you can use the dissolving metal reduction and get the trans alkene. Alright, we have one final reaction to cover in this course, and that's alkylation of alkynes. So we learned way back at the beginning of this course that there's a significant acidity difference for a carbon that's sp3 versus sp2 versus sp. And we attributed that to the fact that an sp carbon, the hybrid orbitals, are much higher in their s character, which means the electrons are more tightly held to the nucleus. And this is true because when we form a cation, generally the cation means we have an empty p orbital. But if we have a carbanion, those usually don't rehybridize. And so that extra s character contained in an sp orbital means that those extra electrons, that negative charge, is more tightly held to the nucleus and is more stable. Now, it doesn't mean that anions of alkynes are stable. They're still very strong bases and good nucleophiles, but they're a lot easier to form than the anions you would get from alkanes or alkenes. So what you can do here with an alkyne, if it's terminal, has to be terminal because you need a hydrogen to remove, is that if you treat it with a strong base, you can remove that hydrogen. And if you then add an alkyl halide to it, the anion that you just formed will attack the carbon because the carbon-halogen bond is polarized, and the halogen gets kicked out. And as a result, we form a new carbon-carbon bond here. Now, there are a lot of limitations on this reaction. So we're going to say that some primary alkyl halides are good electrophiles, but not all of them. In addition, tertiary alkyl halides are terrible, and secondary alkyl halides maybe, maybe not. But the more substituted your alkyl halide gets, the less likely it is to be able to undergo this reaction. So how do you determine whether your alkyl halide will work well for this reaction or not? Well, this first piece of this reaction is just a deprotonation, an acid-base reaction. But the second piece of this reaction is a reaction known as an SN2 reaction. And learning more about the SN2 reaction is what we will do right at the beginning of Organic 2. So to the extent that we can have a cliffhanger for the end of this course, if you want to learn more about why primary alkyl halides, and only some of them work well in this reaction, why secondary and tertiary don't work well for this reaction, you're going to have to come back for Organic 2. But the last thing to work on here is there is one in-class exercise working on reactions of alkynes, so you can work on that, and we'll go over the answers in the next video.